Okay, so you guys, for this part of the lecture, remember, I showed you guys this slide on the covalent bonds. There's a quick peek of your water right there. There's hydrogen gas. And what kind of bonds are those? What kind of bonds are those? Covalent. And what are they doing with their electrons? Sharing. Good. Okay, if the electrons of a bond are not shared equally, such as in water, the bond is called a polar covalent bond, and the molecule is also known as a polar molecule. So right now I want you guys to build water. Each person, there's enough little model pieces in there. Each person build water. You need to know your formula. Okay, so you guys, eyes up here. So if hydrogen was by itself, how many electrons would it have? Hydrogen was all by itself. How many electrons? 1. It's sharing 1 with oxygen, and it's also, you know, they're sharing 2 together because the inner orbital, right, needs 2. So hydrogen, then, what's its ionic charge? That has 1 extra electron. It's positive, okay? Now, over here, how many is oxygen short of a full shell? 2. So oxygen has a -2 charge. Okay, so now hold up your positive charge towards the ceiling of water. So it's the hydrogen side, it's the positive side, right? And then flip it over, and that's your negative side. So do you see how the charge is not evenly distributed around the molecule? Do you guys see what I'm talking about? So this side is negative right here, and this side is, and remember, it's rotating around, but still, no matter how you rotate this thing, one side's always going to be positive and one side's going to be negative. Okay, now, knowing that opposites attract, with your partners, try and align. How would water molecules be next to each other? So just lay them on the table. If you want to hold them up, how would they align? How would water molecules get close to each other? And do you think at times, are they attracted to each other? Do you think they're attracted to each other because this polarity? Okay, looking good, you guys. Sometimes you have to watch out, though. These positives might be a teeny bit too, yeah, there you go. Little, you know, remember, the positive ends or the negative ends are going to repel each other. You guys good with that? Okay, let's move on. I want you guys to build methane. So, is methane a polar molecule or a non-polar molecule? Is it polar like water? Is it polar like water? No, because all the sides on the edges will have a positiveness to it. You guys follow me on that? Okay? Now the thing is, since this whole thing is positive, it really wants nothing to do with water. I guess maybe with a teeny bit of water, maybe it can line up right. But in a bunch of water, there's going to be positive sides that it wants nothing to do with it. Okay? So nonpolar and polar molecules don't mix. Your nonpolar molecules are mostly fuels. Methane's a gas. Actually, this is what you guys fart all the time, is methane gas. And you'll see as we start making some bigger molecules, lots of bonds, because carbon likes to bond to 4 things. So it holds a lot of chemical energy because of those bonds. Okay, I went over this pretty quick. Join me, you guys. With your water molecules, there was a natural attraction between the water molecules if they aligned properly, and they're going to do that. So those bonds are very weak. Lots of times we represent them with a dashed line, but the positive side of the positive hydrogen is attracted to the negative side of anything that's polar. Okay? And these are called hydrogen bonds. They're very important in life, and we'll get to more. We'll talk more about them later. Okay, now ions. Sounds like you guys are already pretty familiar with them. Basically, a lot of things depend on ionic bonds. They dissolve readily, but not in solution. Ionic bonds are strong. For example, salt, NaCl, and salt's hard. Okay, then that leads us to the pH scale. So put your models down. Turn up here, you guys. I'm hoping, again, that this is a review. It says 0, but there really is no 0. It'd just be slightly above 0. So depending on how accurate the reading is, I don't know, maybe you could get something 0.00001 or something, okay? Typically you think of it as 1 through 14, but you can go below 1. Again, you guys should know what's neutral on the scale. The number is what? 7, okay? And the lower numbers are those acids or bases. And so over here is your bases, okay? Now, this has to do with basically how many hydrogen ions are free floating in water versus the OH ions. And then you have just regular water in there that's bonded like your little molecules just going around. But you put things in there like salt or other ions. In the ions also, the ionic bonded things like salt, they dissolve down into their ions. Sodium plus, Cl negative. There's a lot of different salts. Potassium chloride, for example. Okay, so I went over that. I wanted to, but before I go here, okay, so what you guys need to realize is the pH scale, see how it's written? That H actually stands for hydrogen. So it's talking about the number of hydrogen ions. And if there's a lot of hydrogen ions, it's an acid, and it's down in the lower range. So kind of backwards, right? A lot of hydrogen ions, low number. If there's lots of hydrogen ions, then there's not so much hydroxide ions, okay, the OH ions. Notice, right, if you think of water breaking down, can water break down into those? Go ahead. Well, I told you to put your water molecules away. But if you just ripped off one hydrogen, what would you have been left with? An OH, okay? So now, the thing that you guys are more familiar with acids and bases, are they scary? Do you want acid poured on your hand? No, and you don't want a strong base either poured on your hand. Now, a weak one, as you see, is not that bad. But why? Because the solution is not going to be balanced. If it's a strong base, it's going to have a lot of these. If it's a strong acid, it's going to have a lot of these. If those ions are in there, they're going to be attracted to opposites, and they're going to pull things apart, like your skin or your clothing. You guys following me on that? OH makes a wonderful soap because of this. You're pouring a very basic, you're making a basic solution in your laundry when you pour soap in there, which those OHs are attracted to the dirt and the oils and the other things that are in your clothes, pulling them off. The strands of fiber are tougher, and they're going to hold better. But does the wash over time wreck your clothes too? Or for a while, soften them up nicely, right? Because they're deteriorating those particles. So again, you guys are very familiar with them. You could see in the scales right out of your book. See sodium hydroxide, oven cleaner. You guys know how obnoxious that is, right? Hair remover, ammonia, milk of magnesia. We're trying to balance the acid in your stomach. Bleach, phosphates, detergents. And these guys are getting pretty neutral, which you think more of with living things. Seawater, eggs, blood, milk, urine, right? Neutral. Okay, normal rainwater. Now we're getting black coffee, tomatoes, grapes, right? Citric stuff, vinegar, gastric juices. When you throw up and your throat starts to hurt, right? You can even feel the burning. It's because the acid is hitting tissue that's not adapted for having an acid near it. Your stomach has a big mucus lining that keeps the acid from basically eating itself. And then hydrochloric. Okay, so pH influences if reactions can happen easily or not, just like temperature, just like the amount of water that's in the cell. Okay, so it's part of homeostasis, and we'll talk more about that later. Okay, we get to our key vocabulary word, which is what? What's that say up there? Organic. Now, you guys hear this word all the time used in grocery stores incorrectly. Okay? Organic simply means that it's made out of what? What? Carbon. So is every single food item you eat organic? Yes. Now, they have just misused the word to represent farming that's done without added chemicals, okay? But when we say organic in here and in chemistry, it just means a carbon molecule. That's what happens a lot in marketing, is they'll steal scientific words that sound cool, and they'll use them, but then the word loses its real definition, its real meaning. Well, yeah, so you're right, the dictionary evolves, our language evolves because of, new meanings to words. Okay, so now what's so cool about carbon is macromolecules. Because it can make those 4 bonds, like I said, it can make a variety of things. We're going to spend more time with this later, but everybody just kind of acknowledge your 4 macromolecules of life. Say them with me. Now right away, let's try and memorize what this is. Does anybody know? And there's 2 examples of nucleic acids. Anybody remember? That's right. So don't make it harder than it is. That's all we're talking about is DNA and RNA. See the nucleic acid NA. Okay? And then the rest I think you're more familiar with. Okay. So let's go ahead, and you can see what I'm saying, how you can make long chains with carbon. So I want you guys to make glucose. C6H12O6 as a group. As your group, because you don't have enough carbons to do that. Let's go the linear structure to start. Linear structure to start.